Hello there. I'm so glad you found your way here tonight. Wherever you are in the world right now, allow yourself to settle into this shared moment of stillness. Let the noise of the day fade away. Let your thoughts grow quiet, like the gentle hum of distant galaxies drifting through the void. Right now, as you listen to these words, something extraordinary surrounds you. Billions of stars are burning in the darkness. Light from ancient epochs is crossing the universe to reach your eyes. And somehow, from all that cosmic vastness, you are here, listening, wondering. Tonight we journey outward, into the quiet expanse of the cosmos, a universe of galaxies, dark matter, and mysteries that stretch beyond the edge of what we can see. We will explore how the universe was born from a single point smaller than an atom, how space itself is expanding, carrying galaxies apart like leaves on a rising tide, how the faintest glow of ancient light still whispers secrets from the beginning of time. All of it waiting to be shared in the stillness. Tonight, let's drift off together while exploring over 100 soothing facts about cosmology. There's no rush here. No test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the vast universe that holds us all. Either way, this space is for you. There is something profoundly peaceful about contemplating the cosmos. Every fact about the universe is a reminder that we are part of something far greater than ourselves. And it is always expanding, always evolving, always creating new stories written in starlight. You are part of this story. The oxygen in your lungs was forged in ancient stars. The iron in your blood was born in supernova explosions. The atoms that make your cells have been part of nebulae, planets, and creatures that lived billions of years before you were born. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow. And let the weight of the day drift away like starlight fading into the cosmic background. The universe is patient beyond measure. Galaxies form over billions of years without haste. Stars burn for eons before fading into white dwarfs. Black holes wait at the centers of galaxies, patient and eternal. And yet, within all that steadiness, there are sudden bursts of wonder. Supernovae that outshine entire galaxies. Gravitational waves that ripple through space-time. Cosmic rays that race across the universe at nearly the speed of light. Tonight, we will wander through this magnificent outer world. We will meet the forces that shape the cosmos and discover processes that determine the fate of everything that exists. And we will uncover truths about the universe that may surprise even the most curious minds. But there is no hurry. The universe has been expanding for nearly 14 billion years. It can wait a little longer while you rest. Let us begin with the quiet miracle of cosmic creation. The early universe was filled with light so dense, it behaved like matter. In the first moments after the Big Bang, the universe was so extraordinarily hot and dense that photons could not travel freely, but instead formed a plasma that behaved more like a thick luminous fog than empty space, with light passing through it. The energy density of radiation was so high that photons themselves exerted significant gravitational effects, contributing to the curvature of space-time just as matter does. This photon-dominated epoch lasted for roughly 50,000 years, until the universe expanded and cooled enough for matter's gravitational influence to become dominant. During this radiation era, the temperature exceeded billions of degrees, and particles constantly collided with photons, preventing atoms from forming. The transition from radiation domination to matter domination marked a fundamental shift in cosmic evolution, allowing the first structures to begin their slow gravitational collapse. This ancient light energy still exists today, stretched by cosmic expansion into the microwave background radiation that permeates all of space. The idea that light itself could act like matter reveals how extreme the conditions of the early cosmos truly were. The universe began as a point smaller than an atom. Cosmological models suggest that everything in the observable universe, all the matter, energy, space and time that we can detect, was once compressed into a singularity smaller than a subatomic particle. This point of infinite density and temperature contained the seeds of everything that would later become galaxies, stars, planets, and living beings. The Big Bang was not an explosion in space, but rather an explosion of space itself, with the fabric of the cosmos expanding from this inconceivably small origin. At the moment of creation, the laws of physics as we understand them may have been unified into a single force that later separated into gravity, electromagnetism, and the nuclear forces. The temperature at this initial moment is estimated to have exceeded 10 to the power of 32 degrees, conditions under which conventional physics cannot adequately describe what occurred. How such vast complexity could emerge from something smaller than an atom remains one of the deepest mysteries of existence. The entire visible universe, stretching billions of light years across, began as something smaller than the period at the end of a sentence. Time near the Big Bang may have flowed differently than it does now. Einstein's general relativity reveals that time is not a constant, but rather a dimension woven into the fabric of space-time that can be stretched and compressed by gravity and velocity. Near the extreme conditions of the Big Bang, with its inconceivable energy densities and gravitational intensities, time itself may have behaved in ways we cannot fully comprehend using our everyday intuitions. Some theoretical physicists suggest that time as we understand it may have emerged from the Big Bang, along with space, meaning the question of what happened before the Big Bang may be meaningless, because there was no before. Quantum gravity theories propose that at the Planck scale, time becomes fuzzy and indeterminate, losing its familiar one-directional flow. The passage of time in the early universe would have been profoundly affected by the intense gravitational fields of the dense primordial plasma. Our concept of past, present, and future may only make sense in a universe that has expanded and cooled sufficiently for ordinary physics to apply. Time near the cosmic origin remains one of the most profound puzzles at the intersection of physics and philosophy. The universe may have begun as a quantum fluctuation. Quantum mechanics reveals that even empty space is never truly empty, but rather seethes with virtual particles that constantly pop into and out of existence in accordance with the uncertainty principle. Some cosmologists propose that the entire universe may have originated as such a quantum fluctuation, a spontaneous bubble of energy that somehow inflated into the vast cosmos we observe today. This hypothesis suggests that creation required no external cause, but emerged naturally from the probabilistic nature of quantum physics. If space and time can fluctuate into existence, then the universe may have come from literally nothing in the conventional sense. The energy content of the universe may actually sum to zero when gravitational potential energy, which is negative, is balanced against the positive energy of matter and radiation. This remarkable possibility means the universe could be the ultimate free lunch, requiring no net energy input for its creation. While speculative, this quantum origin story connects the largest scales of cosmology with the smallest scales of particle physics. The Planck era remains a mystery we cannot yet solve. The Planck era refers to the first 10 to the negative 43 seconds after the Big Bang, a period so brief and conditions so extreme that our current understanding of physics completely breaks down. During this epoch, the universe was smaller than the Planck length of about 10 to the negative 35 meters, a scale at which quantum effects and gravity become equally important and cannot be treated separately. To describe this era properly, physicists would need a complete theory of quantum gravity that successfully unifies general relativity with quantum mechanics, something that remains one of the greatest unsolved problems in physics. Temperature during the Planck era exceeded the Planck temperature of about 10 to the 32 degrees, conditions under which the four fundamental forces may have been unified into a single superforce. All current observations and calculations about the early universe begin after this mysterious epoch, leaving the true origin moment shrouded in theoretical uncertainty. String theory, loop quantum gravity, and other approaches attempt to penetrate this barrier, but none has yet achieved definitive success. The Planck era represents the ultimate frontier of cosmological knowledge, the boundary beyond which our physics cannot yet see. The universe expanded faster than light in its first fraction of a second. During the epoch of cosmic inflation, which occurred within the first trillionth of a trillionth of a trillionth of a second after the Big Bang, space itself expanded at a rate far exceeding the speed of light. This does not violate Einstein's relativity because the speed limit applies to objects moving through space, not to space itself stretching. In this brief moment, the universe grew from smaller than a proton to potentially larger than the observable universe today, a factor of at least 10 to the 26 in size. This exponential expansion was driven by a hypothetical field called the inflaton, which released enormous amounts of energy as it decayed. Inflation explains why the universe appears so uniform in all directions, despite regions that could never have communicated at light speed. It also stretched tiny quantum fluctuations into the seeds that would eventually grow into galaxies and galaxy clusters. This burst of superluminal expansion remains one of the most dramatic events in cosmic history. Some regions of the cosmos may still be inflating forever. The theory of eternal inflation proposes that while our observable universe stopped inflating and settled into normal expansion, other regions of space may continue to inflate forever, spawning new pocket universes in an endless process. In this picture, inflation is not a single event that ended, but an ongoing phenomenon, with our universe representing just one bubble in an eternally frothing cosmic foam. These other inflating regions would be forever beyond our ability to observe or contact, separated by distances expanding faster than light can traverse. The physical laws and constants in these other pocket universes might differ from our own, determined by how the inflaton field decayed in each region. Eternal inflation suggests that the cosmos may be far larger and more varied than the mere 93 billion light-years of our observable universe. This perspective transforms the Big Bang from a unique beginning into just one of countless creation events occurring perpetually. If eternal inflation is correct, the universe as a whole has no beginning and no end, but exists in a state of perpetual self-reproduction. Inflation explains why distant parts of the universe look alike. One of the great puzzles of cosmology, known as the horizon problem, asks why regions of the universe on opposite sides of the sky have nearly identical temperatures, despite being too far apart to have ever exchanged information at the speed of light. Cosmic inflation solves this puzzle by proposing that these distant regions were once in contact before the universe underwent its explosive expansion phase. Before inflation, the universe was small enough that its different parts could reach thermal equilibrium, sharing the same temperature and density. The subsequent inflationary expansion then stretch these once connected regions to opposite ends of the observable universe while preserving their similarity. This explanation is remarkably elegant, reducing what seemed like an improbable coincidence to a natural consequence of early cosmic dynamics. The uniformity of the cosmic microwave background radiation, uniform to 1 part in 100,000, provides strong evidence that inflation or something like it actually occurred. Inflation thus reveals that the vast distances separating cosmic regions today mask a shared origin in the first moments of existence. Inflation predicts the universe is nearly perfectly flat. Geometrically, the universe could be curved like the surface of a sphere, saddle-shaped like a hyperbolic surface, or flat like an infinite plane. And this geometry depends on the total energy density relative to a critical value. Cosmic inflation makes the remarkable prediction that regardless of how curved the universe was initially, the exponential expansion would have stretched any curvature to near flatness, just as inflating a balloon makes its surface appear increasingly flat to an ant. Observations of the cosmic microwave background, supernovae, and galaxy distributions all confirm that the universe is indeed flat too, within the precision of our measurements, with any deviation from perfect flatness being less than about 0.5%. This flatness is one of the key predictions that inflation gets spectacularly right, providing strong support for the inflationary paradigm. A perfectly flat universe has implications for its ultimate fate, suggesting it will expand forever, rather than collapsing back in a big crunch. The energy density of the universe balances gravity so precisely that expansion continues indefinitely at an ever-slowing rate. This cosmic flatness is one of the most precisely measured and tested predictions in all of cosmology. Quantum fluctuations may have seeded every star and planet. During inflation, quantum mechanical effects caused tiny random fluctuations in the energy density of space, variations that would normally have been inconsequentially small on everyday scales. The exponential expansion of inflation stretched these microscopic quantum ripples into macroscopic density variations spanning vast cosmic distances. When inflation ended, these stretched fluctuations became slight variations in the density of matter and energy, regions that were slightly denser than average, and regions that were slightly less dense. Over billions of years, gravity amplified these initial seeds as denser regions attracted more matter and grew into galaxies, galaxy clusters, and the cosmic web. Every star, planet, and living being that exists today can trace its origins back to these primordial quantum fluctuations frozen into the fabric of space by inflation. The pattern of hot and cold spots in the cosmic microwave background radiation directly reflects these original quantum seeds. The idea that the largest structures in the universe grew from quantum uncertainty is one of the most profound connections between the very small and the very large. Cosmic inflation could have spawned an infinite multiverse. If the inflationary mechanism that created our universe is correct, it naturally leads to the possibility of a multiverse containing an infinite number of separate universe bubbles, each with potentially different physical properties. In eternal inflation, quantum fluctuations cause some regions of the inflating space to stop inflation and form pocket universes like ours, while other regions continue inflating forever, constantly spawning new bubbles. The physical constants and laws in each bubble universe may be determined by random processes during the decay of the inflaton field, meaning other universes could have different particle masses, force strengths, or even dimensions. This multiverse perspective changes deep questions about why our universe has the properties it does, since if all possible universes exist, we necessarily find ourselves in one compatible with our existence. The inflationary multiverse remains beyond direct empirical testing, since other bubbles are forever outside our cosmic horizon. However, if certain patterns were found in the cosmic microwave background, they might hint at collisions between our bubble and others. The multiverse remains one of the most controversial and philosophically profound implications of inflationary cosmology. The cosmic background radiation once glowed bright orange in the sky. When the cosmic microwave background radiation was first released about 380,000 years after the Big Bang, it would have been visible to any hypothetical observer as a brilliant orange glow filling the entire sky. At that moment, the universe had cooled to about 3,000 degrees Kelvin, the temperature at which hydrogen atoms could finally form and light could travel freely for the first time. This primordial light was not the faint microwave radiation we detect today, but rather the warm glow of a cooling cosmos, similar in color to a hot ember or the surface of a red dwarf star. Over the 13 billion years since that moment, the expansion of the universe has stretched these light waves by a factor of about 1100, cooling them from visible orange light to invisible microwaves. If you could somehow travel back to that epoch, you would find yourself immersed in a universe-spanning orange glow, with no stars or galaxies yet formed. The cosmic microwave background remains the oldest light in the universe, a fossil record of the moment when space first became transparent. This ancient glow now fills all of space as a cold bath of microwave radiation, just a few degrees above absolute zero. The universe once transitioned from opaque to transparent. For the first few 100,000 years after the Big Bang, the universe was completely opaque, filled with a hot plasma of free electrons that scattered light and prevented photons from traveling any significant distance. This era is sometimes called the Cosmic Dark Ages, though paradoxically the universe was filled with brilliant light that simply could not escape from the plasma fog. When the cosmos cooled to about 3,000 degrees Kelvin, electrons finally slowed enough to be captured by atomic nuclei, forming neutral hydrogen in an event called recombination. With free electrons no longer available to scatter photons, light suddenly could travel unimpeded across the universe for the first time. This transition from opaque to transparent happened relatively quickly on cosmic timescales, taking perhaps 80,000 years to complete throughout the observable volume. The light released at this moment has been traveling ever since, and forms the cosmic microwave background we detect today. This transition was the birth of light travel in the universe, the moment when the cosmos opened its eyes to itself. The cosmic microwave background is nearly uniform to 1 part in 100,000. When scientists measure the temperature of the cosmic microwave background from different directions in the sky, they find it is astonishingly uniform at about 2.7 Kelvin, with variations of only about 100 millionths of a degree from place to place. This extraordinary uniformity across the entire observable universe is far more precise than could occur by chance if distant regions had never been in contact. The tiny variations that do exist, at the level of 1 part in 100,000, represent the seeds of all cosmic structure, the slightly denser and less dense regions that would eventually grow into galaxies and voids. Mapping these minuscule temperature fluctuations has become one of the most important observational programs in cosmology, with satellites like COBE, WMAP, and Planck providing increasingly detailed pictures. The statistical properties of these fluctuations match the predictions of inflationary theory with remarkable precision. These measurements tell us about the geometry, composition, and age of the universe with unprecedented accuracy. The uniformity of the cosmic microwave background is one of the strongest pieces of evidence for the Big Bang model of cosmic origins. Those tiny differences seeded galaxies. The minuscule temperature variations in the cosmic microwave background, at the level of 1 part in 100,000, represent the primordial density fluctuations that gravity would amplify over billions of years into every galaxy, star, and planet that exists today. Regions of the early universe that were slightly denser than average exerted slightly stronger gravitational attraction, drawing in more matter over time and growing ever denser. Regions that were slightly less dense lost matter to their neighbors, and eventually became the vast cosmic voids between galaxy filaments. This process of gravitational amplification is called hierarchical structure formation, with small overdensities merging into larger ones as the universe evolved. Computer simulations that start with the observed pattern of cosmic microwave background fluctuations and evolve them forward in time produce galaxy distributions that match what telescopes actually observe. Without these initial seeds, the universe would have remained a smooth, featureless fog of atoms forever, with no stars to light the darkness or planets to harbor life. Every structure in the cosmos, from superclusters of galaxies down to individual solar systems, represents the gravitationally amplified descendant of a primordial quantum fluctuation. Patterns in the cosmic microwave background hint at ripples from before the Big Bang. Some cosmologists have searched the cosmic microwave background for patterns that might reveal physics from before the conventional Big Bang, remnants of an earlier phase of cosmic evolution. Certain theoretical models, such as cyclic cosmologies or conformal cyclic cosmology proposed by Roger Penrose, predict specific signatures that could survive the transition between cosmic epochs. Some analyses have claimed to find circular patterns or unusual correlations that might represent collisions with other universe bubbles or echoes from a previous aeon. These claims remain highly controversial, with many scientists arguing that the proposed patterns could be statistical flukes or artifacts of the analysis methods. If confirmed, such features would revolutionize our understanding of cosmic origins, suggesting the Big Bang was not the absolute beginning, but rather a transition between phases. The search for pre-Big Bang signatures represents one of the most speculative frontiers of observational cosmology. Whether the cosmic microwave background truly preserves memories from before our universe's birth remains an open and tantalizing question. The cosmic microwave background is dotted with strange cold spots. Among the tiny temperature fluctuations in the cosmic microwave background, certain anomalies have attracted particular attention, including an unusually large cold spot in the southern constellation Eridanus that appears significantly colder than expected from standard cosmological models. This cold spot spans about 5 degrees of sky, corresponding to a region about 1 billion light-years across, and shows a temperature depression of roughly 70 millionths of a degree below the average. Some astronomers suggested this cold spot might be explained by a supervoid, an exceptionally large region of space with fewer galaxies than average, which would cause passing light to lose extra energy. However, subsequent surveys have not found a supervoid large enough to fully explain the observed cold spot, leaving its origin somewhat mysterious. Other explanations propose the cold spot could be a remnant of cosmic inflation, a statistical fluctuation, or even evidence of a collision with another universe bubble. These cosmic microwave background anomalies challenge our understanding and may contain clues to new physics. The cold spot remains one of the most debated features in the map of the early universe. The cosmic microwave background once fit inside your hand. Before inflation, the entire region of space that would eventually become the observable universe, now spanning 93 billion light-years, was compressed into a volume smaller than a proton. At that moment, all the energy that would become the cosmic microwave background was concentrated in this inconceivably tiny space. As the universe expanded, this primordial energy stretched across ever larger volumes, eventually filling the cosmos we observe today. By the time the cosmic microwave background was released at recombination, the observable universe had expanded to roughly 40 million light-years across, still vastly smaller than today. The total energy in the cosmic microwave background has remained essentially constant, but its density has decreased as space has expanded. Today, every cubic centimeter of space contains roughly 400 cosmic microwave background photons, remnants of that ancient epoch of creation. The idea that all the light now filling the universe once occupied a space you could cup in your hands captures the staggering scales of cosmic evolution. The universe's geometry may be ever so slightly curved. Although observations indicate the universe is extremely close to geometrically flat, the measurements have finite precision and allow for a tiny amount of either positive or negative curvature that would be undetectable with current instruments. If the universe has slight positive curvature, like the surface of a four-dimensional sphere, then traveling far enough in any direction would eventually bring you back to your starting point, and the universe would have a finite total volume, despite having no edges. If the curvature is slightly negative, like a four-dimensional saddle, the universe would be infinite, and space would have unusual geometric properties, where parallel lines eventually diverge. The curvature is determined by the total energy density of the universe compared to a critical value, and observations constrain any deviation from flatness to less than about 0.5%. Future observations with even greater precision may eventually detect a tiny curvature or confirm that the universe is perfectly flat to an even higher degree. The geometry of the universe has profound implications for its origins, structure, and ultimate fate. Whether the cosmos curves back on itself or extends forever in all directions remains one of the deepest questions in cosmology. The observable universe is only a fraction of the whole. The observable universe extends about 46 billion light-years in every direction, bounded by the cosmic horizon beyond which light has not had time to reach us since the Big Bang. This observable region contains roughly 2 trillion galaxies, but it represents only a small patch of a potentially infinite whole. If cosmic inflation is correct, the total universe may be vastly larger than what we can observe, perhaps by factors of 10 to the power of 23 or more. Some inflationary models suggest the entire cosmos could be effectively infinite, making our observable universe an infinitesimally small bubble within boundless space. The regions beyond our cosmic horizon are forever inaccessible to observation, because the expansion of space carries them away faster than light can traverse the distance. Everything we know about cosmology, every galaxy count and structure map, applies only to our limited observable patch. The true size and extent of the complete universe may be something we can never directly know. The cosmic horizon keeps expanding, but light speed keeps us bounded. The cosmic horizon represents the maximum distance from which light has had time to reach Earth since the beginning of the universe, and as time passes, this horizon continuously grows, bringing previously unseen regions into view. However, the accelerating expansion of the universe driven by dark energy means that while our horizon grows, distant galaxies are being carried away from us faster than light can bring them closer. Eventually, the expansion will win, and galaxies currently visible will fade beyond our horizon, as the light they emit can no longer overcome the stretching of space. In the far future, observers in our galaxy will see fewer and fewer external galaxies, until eventually the night sky contains only our local gravitationally bound group. The cosmic horizon is not a physical barrier, but rather a limit set by the finite speed of light and the finite age of the universe. New light is always arriving from slightly more distant sources, expanding our view at the speed of light. Yet the accelerating expansion ensures that most of the universe will forever remain beyond our reach. The speed of light sets a limit on what we can know. The speed of light serves as a cosmic speed limit that fundamentally constrains our ability to gather information about the universe. since no signal can travel faster than approximately 300,000 kilometers per second. This limit means we can only see events whose light has had time to reach us, creating the cosmic horizon that bounds our observable universe. Events occurring beyond this horizon are as inaccessible to us as if they did not exist, since their influence cannot reach Earth within the age of the cosmos. The finite speed of light also means we see the universe not as it is now, but as it was when the light we observe began its journey, looking billions of years into the past when we observe distant galaxies. If intelligent beings exist in galaxies beyond our cosmic horizon, we could never know of their existence or communicate with them, regardless of how advanced our technology becomes. The speed of light transforms the universe from a potentially knowable whole into a series of isolated patches, each with its own observable horizon. This cosmic loneliness is written into the fundamental physics of relativity. There may be more galaxies in the observable universe than grains of sand on Earth. Astronomers estimate that the observable universe contains roughly 2 trillion galaxies, a number so vast it may exceed the total number of sand grains on all the beaches and deserts of Earth. Each of these galaxies contains anywhere from millions to hundreds of billions of stars, bringing the total stellar population to a number with more than 20 zeros. Most of these galaxies are too faint and distant to be detected by current telescopes, with estimates based on extrapolations from deep survey observations and theoretical models. The galaxy count has been revised upward several times as observations have improved, and the true number may be even higher than current estimates suggest. If each galaxy averaged 100 billion stars, the total number of stars in the observable universe would be around 200 billion trillion. The comparison to sand grains helps make this incomprehensible vastness slightly more tangible, though even this comparison strains the imagination. Every point of light in the night sky represents just the nearest fraction of this cosmic multitude. Superclusters of galaxies weave a cosmic web across the universe. The universe on its largest scales is not uniformly filled with galaxies, but instead displays a web-like structure where galaxies cluster along filaments and sheets surrounding vast empty voids. These filaments and walls form a foam-like pattern stretching across hundreds of millions of light-years, with the densest concentrations of galaxies occurring at the nodes where multiple filaments intersect. This cosmic web is the largest organized pattern in nature, dwarfing even the largest individual structures like superclusters and galaxy groups. The web structure arises naturally from the gravitational amplification of primordial density fluctuations, with matter flowing from voids into filaments, and from filaments into nodes over cosmic time. Computer simulations of cosmic evolution, starting from initial conditions measured in the cosmic microwave background, successfully reproduce the observed web structure. Surveys mapping millions of galaxy positions have confirmed the reality of this cosmic web and revealed its statistical properties in exquisite detail. The web continues to evolve today, with filaments growing denser as galaxies continue their slow gravitational drift toward the highest concentrations of matter. Galaxy filaments can stretch for 500 million light-years. The filaments that form the scaffolding of the cosmic web can extend for truly staggering distances, with some stretching across 500 million light-years or more of intergalactic space. These are the largest coherent structures in the observable universe, chains and walls of galaxies that dwarf even the largest galaxy clusters. The Sloan Great Wall, discovered in the early 2000s, spans approximately 1.4 billion light-years and contains hundreds of thousands of galaxies along its length. More recently, even larger structures have been identified, including the Hercules Corona Borealis Great Wall, which may extend for 10 billion light-years, or about a tenth of the observable universe. These immense structures formed as gravity slowly drew matter together, along the lines where primordial density fluctuations happened to be slightly enhanced. Despite their size, the filaments contain relatively thin concentrations of matter compared to the vast voids they surround. The existence of structures on such enormous scales was once surprising to cosmologists, but is now understood as a natural consequence of hierarchical structure formation. The largest known structure is a billion light-year-long wave of galaxies. The largest structures identified in the observable universe extend for billions of light-years, challenging earlier assumptions about the maximum size that cosmic structures could reach. The Hercules Corona Borealis Great Wall, identified through analysis of gamma-ray burst locations, may span approximately 10 billion light-years, making it the largest known structure in the observable universe. Such enormous structures approach the homogeneity scale, the size above which the universe should appear smooth and uniform according to the cosmological principle. Some scientists have questioned whether these truly represent coherent structures or merely patterns that arise from the way surveys map clustering. If these structures are real and gravitationally bound, they pose interesting puzzles for cosmology, since there has been limited time since the Big Bang for gravity to assemble them. The discovery of ever larger structures has pushed back estimates of the homogeneity scale and refined our understanding of cosmic evolution. Whether even larger structures await discovery beyond these known giants remains an open question. The cosmic web resembles the neural structure of a brain. Scientists have noted a striking visual and mathematical similarity between the large-scale structure of the cosmic web and the network of neurons in the human brain, despite the vast difference in scale between them. Both systems display a web-like pattern of nodes connected by filaments, with dense clusters at intersection points and sparse regions in between. The cosmic web spans about 100 billion light-years across its observable extent, while the neural network of the brain fits within a volume of about 15 centimeters, yet their topological structures share remarkable features. Studies comparing the two have found similar levels of complexity, clustering, and network organization in both systems. This similarity is likely coincidental rather than evidence of any deeper connection, arising because both systems are shaped by similar physical principles of network formation and self-organization. However, the comparison captures the imagination and suggests that certain structural patterns may be universal across vastly different scales. The cosmic web and the thinking brain both represent nature's tendency to build complex interconnected networks. The cosmic web keeps growing as galaxies drift apart. The cosmic web is not a static structure but continues to evolve as the expansion of the universe stretches. The filaments and voids grow ever larger. Within filaments and clusters, gravity remains strong enough to counteract cosmic expansion, holding galaxies in gravitationally bound groups that orbit their common centers. However, the voids between filaments are expanding under the influence of dark energy, causing the overall web pattern to stretch and thin over cosmic time. Galaxies within filaments continue to drift toward the densest nodes where galaxy clusters reside, slowly increasing the contrast between dense regions and empty voids. In the far future, the expansion driven by dark energy will eventually isolate galaxy groups from one another as the distances between them grow faster than light can traverse. The cosmic web as we observe it today represents a snapshot in a continuous evolutionary process that began with tiny density fluctuations and will end with isolated island universes separated by vast expanding voids. This slow cosmic dance of attraction and expansion shapes the largest patterns in existence. Cosmic voids are vast expanses with almost no galaxies that are still expanding. Cosmic voids are enormous regions of space containing far fewer galaxies than average, spanning hundreds of millions of light-years across and occupying most of the universe's volume. While filaments and clusters contain the majority of galaxies, voids make up roughly 50 to 60% of the total volume of the cosmos. These voids are not completely empty, but contain a sparse scattering of galaxies and diffuse intergalactic gas at densities far below the cosmic average. Unlike the filaments where gravity has pulled matter together, voids are regions from which matter has been evacuating for billions of years, flowing toward the denser surrounding structures. Because voids contain less matter, they expand slightly faster than the average rate of cosmic expansion, growing ever larger over time. Eventually, the largest voids may merge as the walls between them thin and break, creating even more enormous empty regions. Voids represent the cosmic complement to the web of filaments and clusters, the negative space that makes the web structure possible. Supervoids may cause subtle distortions in cosmic light. When light from the cosmic microwave background passes through a supervoid, it can experience a subtle energy shift caused by the changing gravitational potential of the void as the universe expands. As a photon enters a void, it gains energy climbing into the gravitational well, but by the time it exits, cosmic expansion has weakened the gravitational potential, meaning it loses less energy climbing out than it gained falling in. This integrated Sachs-Wolf effect causes photons passing through voids to appear slightly warmer than those that travel through average regions of space. The effect is subtle, contributing only a few millionths of a degree to the cosmic microwave background temperature. But it has been detected statistically by correlating temperature maps with surveys of galaxy distributions. Supervoids like the one proposed to explain the Eridanus cold spot might cause the opposite effect under certain conditions, making the mysteries of these giant empty regions even more complex. Studying light distortions from voids provides a unique probe of dark energy and cosmic expansion. The subtle imprints of emptiness on the oldest light in the universe reveal secrets about both. The integrated Sachs-Wolf effect reveals dark energy's fingerprints. The integrated Sachs-Wolf effect is a phenomenon where the cosmic microwave background photons gain or lose energy as they pass through the time-varying gravitational potentials of cosmic structures. In a universe without dark energy, the gravitational potentials of structures would remain relatively stable, and the energy gained entering a potential well would equal the energy lost exiting it. However, dark energy causes the universe's expansion to accelerate, which stretches and weakens the gravitational potentials over time, creating the net energy change that produces the effect. By correlating cosmic microwave background temperature maps with maps of galaxy concentrations, scientists have detected this effect and confirmed its consistency with dark energy predictions. The integrated Sachs-Wolf effect provides one of several independent lines of evidence that dark energy exists and is causing the cosmic expansion to accelerate. This subtle imprint on the oldest light in the universe carries information about conditions in the relatively recent cosmos. The detection of dark energy's fingerprints in the cosmic microwave background demonstrates the interconnection of physics across vast stretches of cosmic history. We may live in a local bubble of unusually empty space. Some observations suggest that our region of the universe, extending perhaps 200 to 300 million light-years around us, may be somewhat underdense compared to the cosmic average, a local void or bubble in the cosmic web. If this local hole exists, it would affect our measurements of cosmic expansion, potentially explaining some of the tension between different methods of measuring the Hubble constant. Matter flowing out of this local underdense region toward the surrounding overdense walls and filaments could add an extra apparent acceleration to our observations of distant galaxies. Some cosmologists have proposed that a significant local void could even explain observations currently attributed to dark energy, though this hypothesis remains controversial, and faces challenges matching all available data. The existence and extent of this local underdensity continues to be studied through galaxy surveys and other observations. Our position within any cosmic structure affects our view of the universe, making it important to understand our local environment. Whether we inhabit a particularly empty corner of the cosmos remains an intriguing question, with implications for precision cosmology. Dark matter may clump into invisible filaments that shape galaxies. Dark matter, which comprises roughly 27% of the universe's total mass energy, is believed to form the invisible scaffolding on which ordinary matter collects to build galaxies and cosmic structures. Computer simulations of cosmic evolution show dark matter forming a vast web of halos and filaments that gravitationally guides the distribution of visible matter. Galaxies form preferentially within dense dark matter halos, with the largest galaxies sitting at the centers of the most massive halos. The dark matter filaments connecting halos provide pathways along which galaxies migrate over cosmic time, channeling the slow assembly of galaxy clusters. Without dark matter's gravitational influence, the primordial density fluctuations would not have had sufficient gravitational amplification to form galaxies before the universe expanded too much. The distribution of dark matter has been mapped indirectly through gravitational lensing, revealing halos and filaments that match simulation predictions remarkably well. Dark matter remains invisible and mysterious in its nature, yet its gravitational influence shapes everything visible in the cosmos. The bullet cluster provides direct evidence for dark matter. The bullet cluster is a pair of galaxy clusters that collided roughly 150 million years ago, providing one of the most compelling pieces of evidence that dark matter is a real substance rather than a modification of gravity. When the clusters collided, the hot intergalactic gas from each cluster interacted and slowed down, piling up in the collision zone, where it can be detected through its X-ray emission. However, gravitational lensing maps reveal that most of the mass in each cluster passed through the collision without slowing, remaining centered on the galaxies rather than the gas. This separation between the visible matter dominated by gas and the gravitationally dominant invisible matter is exactly what dark matter theory predicts, but is very difficult to explain with modified gravity alternatives. The dark matter halos of each cluster simply passed through one another like two ghostly clouds, unimpeded by electromagnetic interactions. The bullet cluster has become an iconic example cited in discussions of dark matter evidence. Subsequent observations of other colliding clusters have confirmed this separation pattern, strengthening the case for dark matter as a real particle. Axions, if they exist, could make up all dark matter. Axions are hypothetical lightweight particles originally proposed to solve a puzzle in particle physics, but now considered leading candidates for the mysterious dark matter that dominates the mass of the universe. If axions exist with the properties theorists predict, they would have been produced abundantly in the early universe, and would today form a cold, invisible gas pervading galaxies and intergalactic space. Axions would interact extremely weakly with ordinary matter through gravity and a tiny electromagnetic coupling, making them extraordinarily difficult to detect directly. Several experiments around the world are attempting to detect axions by looking for their conversion into photons in the presence of strong magnetic fields. If axions are discovered, they would simultaneously solve two major mysteries in physics: the nature of dark matter and the strong CP problem in quantum chromodynamics. The mass of axions is poorly constrained theoretically, with different models predicting vastly different detection requirements. Whether these ghostly particles truly pervade the cosmos awaits experimental confirmation. Primordial black holes could explain dark matter. Some cosmologists have proposed that dark matter might not be an exotic new particle at all, but rather a population of black holes formed in the early universe from the collapse of extremely dense regions. These primordial black holes would have formed before the first stars, arising from density fluctuations that exceeded a critical threshold during inflation or phase transitions. If they exist in sufficient numbers, and with appropriate masses, primordial black holes could account for all or part of the observed dark matter. Observations constrain the allowed mass range for primordial black holes as dark matter, ruling out many but not all possibilities through effects like gravitational lensing, cosmic microwave background distortions, and gravitational wave detections. The detection of gravitational waves from merging black holes by LIGO revived interest in primordial black holes when some of the detected masses seemed unexpected from conventional stellar evolution. However, distinguishing primordial black holes from those formed by stellar collapse remains challenging. Whether ancient black holes from the dawn of time lurk invisibly throughout the cosmos is an intriguing question still under investigation. Some stars may have formed directly from collapsing dark matter. Theoretical studies have speculated about the possibility of dark stars, hypothetical stellar objects powered not by nuclear fusion but by the annihilation of dark matter particles in their cores. In the early universe, if dark matter consists of weakly interacting massive particles that can annihilate when they encounter their antiparticles, extremely dense regions might have powered primitive stars through this exotic energy source. These dark stars would have been enormous compared to ordinary stars, potentially thousands of times more massive than the Sun, and millions of times more luminous, yet relatively cool at their surfaces. As the universe aged and dark matter became less concentrated, these dark stars would have run out of fuel and either collapsed into black holes or transitioned to ordinary fusion-powered burning. No dark stars have been definitively observed, and the hypothesis depends on specific assumptions about dark matter's properties that remain unconfirmed. If they did exist, dark stars might have seeded the formation of the supermassive black holes now found at the centers of galaxies. The possibility of dark matter directly powering stellar objects remains one of the more speculative ideas in cosmic evolution. The vacuum of space may not be empty, but simmering with quantum energy. Quantum mechanics predicts that even completely empty space is filled with a seething foam of virtual particles that constantly pop into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating. This quantum vacuum energy gives empty space a baseline energy density that, according to quantum field theory, should be enormous, vastly greater than observed. The discrepancy between theoretical predictions of vacuum energy and the measured value of dark energy is one of the largest unsolved problems in physics, with predictions exceeding observations by some 120 orders of magnitude. This cosmological constant problem suggests either our understanding of quantum vacuum energy is fundamentally incomplete, or some unknown mechanism cancels most of this energy. Despite the puzzle of its magnitude, vacuum energy, with properties similar to those predicted, may be what we observe as dark energy driving cosmic acceleration. The idea that empty space hums with quantum energy transforming the fate of the universe is one of the strangest implications of modern physics. The vacuum is far from nothing, potentially containing the dominant energy component of the entire cosmos. Dark energy might grow stronger with time, changing the universe's destiny. While current observations are consistent with dark energy being a cosmological constant with unchanging energy density, some theoretical models propose that dark energy could evolve over time, potentially growing stronger or weaker as the universe ages. If dark energy increases in strength, a scenario called phantom energy, the cosmic expansion would accelerate even more rapidly, eventually tearing apart galaxies, stars, planets, and even atoms in a cataclysmic Big Rip. Conversely, if dark energy weakens over time, the expansion might eventually slow enough for gravity to halt the expansion or even reverse it into a big crunch. Distinguishing between these possibilities requires extremely precise measurements of cosmic expansion at different epochs, a challenge that current and future surveys are designed to address. The equation of state of dark energy, the ratio of its pressure to its energy density, is the key parameter that determines whether it is constant or evolving. Current measurements constrain this parameter to be very close to -1, consistent with a cosmological constant, but small deviations could have enormous implications. The ultimate fate of the universe hangs on the subtle properties of this mysterious component. Vacuum energy could drive inflation and dark energy alike. Cosmologists have noted intriguing similarities between the mechanism thought to have driven cosmic inflation in the first instance after the Big Bang, and the dark energy currently accelerating the universe's expansion. Both phenomena involve a form of energy pervading empty space that causes exponential or accelerating expansion by exerting negative pressure. During inflation, the energy density of the inflaton field was vastly higher than today's dark energy, driving expansion at truly stupendous rates before decaying into normal matter and radiation. Dark energy today has much lower energy density, but acts on much longer timescales, gradually accelerating the cosmic expansion over billions of years. Some theorists propose that inflation and dark energy might be manifestations of the same underlying physics, perhaps different phases of a single scalar field. If a connection exists, understanding dark energy might illuminate the physics of inflationary acceleration, and vice versa. The possibility that the same fundamental mechanism shaped both the birth and the current evolution of the cosmos is a tantalizing hint of deep unity. The speed of cosmic expansion has changed more than once. The history of cosmic expansion is not one of steady growth, but rather a story of dramatic shifts, as different components of the universe have dominated at different epochs. In the first instant, inflation drove exponentially rapid expansion, before the inflaton field decayed and released its energy as matter and radiation. For the next roughly 50,000 years, radiation dominated and the expansion gradually slowed as gravity from the dense cosmic plasma fought against outward momentum. After matter came to dominate, the expansion continued to slow but at a gentler rate as the universe cooled and thinned. Then, around 5 billion years ago, the slowing reversed as dark energy became the dominant component, initiating the current epoch of accelerating expansion that will continue into the far future. Each transition between radiation domination, matter domination, and dark energy domination left signatures in the cosmic microwave background and large-scale structure that cosmologists use to reconstruct this history. The universe has danced between slowing and accelerating, a cosmic rhythm set by the changing balance of its constituent energies. The first stars may have been hundreds of times heavier than the Sun. The first stars that formed in the universe, known as population 3 stars, are theorized to have been massive giants, reaching hundreds of times the mass of our Sun, far larger than typical stars born today. These primordial stars formed from clouds of pure hydrogen and helium, the only elements present after the Big Bang, without the heavier elements that help modern gas clouds fragment and cool efficiently. Without efficient cooling, the gas clouds that formed the first stars remained hotter and more massive before finally collapsing, producing enormous stellar behemoths. These population 3 stars would have burned through their nuclear fuel in just a few million years, ending their brief lives in spectacular supernova explosions or direct collapse into black holes. Their violent deaths seeded the universe with the first heavy elements, enriching the gas from which subsequent generations of stars would form. no population 3 stars have been directly observed, as they all died long ago in the young universe, but their fingerprints may remain in the oldest surviving stars. The search for evidence of these first cosmic giants continues through observations of extremely metal-poor stars and distant quasars. Some of those stars may have collapsed into the first black holes. When the most massive population 3 stars exhausted their nuclear fuel after just a few million years, some may have collapsed directly into black holes without undergoing supernova explosions that would have ejected their material into space. These direct collapse black holes could have been born with masses of tens to hundreds of solar masses, providing seeds for the supermassive black holes that would eventually grow to dominate galaxy centers. The formation of massive black holes so early in cosmic history helps explain how supermassive black holes weighing billions of solar masses had already formed by the time the universe was less than 1 billion years old. Some theories propose that even more massive direct collapse black holes could have formed from the collapse of massive primordial gas clouds before the first stars ignited. These seed black holes would have grown through mergers and accretion, consuming surrounding gas and smaller black holes over billions of years. The origin of supermassive black holes remains one of the key unsolved problems in astrophysics, with the first stars likely playing a crucial role. The earliest black holes represent the connection between the first cosmic light and the dark hearts of galaxies. The reionization era lit up space with the first galaxies. After the cosmic microwave background was released and the universe entered its dark ages without sources of light, the first stars and galaxies gradually began to form and emit radiation that would transform the cosmos once again. This radiation, particularly the ultraviolet light from hot young stars, was energetic enough to strip electrons from the neutral hydrogen atoms that filled intergalactic space in a process called reionization. Over a period of perhaps 500 million years, the expanding bubbles of ionized gas around the first galaxies gradually merged until the entire intergalactic medium was once again ionized, as it remains today. The reionization era represents the cosmic dawn, the transition from a universe filled with neutral gas to one pervaded by a hot, ionized plasma, maintained by the ongoing starlight from billions of galaxies. Observations of the most distant quasars and galaxies probe this era, revealing signatures of the patchy reionization process in their spectra. The James Webb Space Telescope is now observing galaxies from this cosmic dawn, providing new insights into the objects that lit up the early universe. Reionization marks the moment when the universe awoke from darkness and began filling with the starlight that has continued to this day. Ancient quasars shine from less than 1 billion years after the Big Bang. Quasars are the extremely luminous cores of galaxies, powered by supermassive black holes, actively consuming surrounding gas, and some of the most distant quasars observed shine from a time when the universe was less than 1 billion years old. These ancient quasars contain black holes weighing billions of solar masses, a puzzling finding since there seems to have been insufficient time for them to grow so massive through ordinary accretion processes. The most distant quasars provide valuable probes of the early universe, their light revealing information about the intergalactic medium, reionization history, and early chemical enrichment, as it passes through billions of light-years of intervening space. Each newly discovered record-breaking quasar pushes back our understanding of when complex cosmic structures first arose. The host galaxies surrounding these ancient quasars are now being studied with the most powerful telescopes, revealing insights into early galaxy formation and evolution. How such massive black holes formed so quickly remains one of the key puzzles driving research into the first generations of stars and cosmic structure formation. These beacons from the cosmic dawn illuminate both the light and the dark during the universe's formative epoch. Some ancient stars may still burn from the dawn of time. While the most massive early stars burned out quickly, the smallest stars from the earliest generations could theoretically still be shining today if they had masses less than about 80% of the Sun, and thus burn their fuel extremely slowly. These hypothetical survivors would be extremely old red dwarf stars, whose composition would reveal their ancient origins through an almost complete absence of elements heavier than hydrogen and helium. Astronomers have searched for such extremely metal-poor stars in the halo of our galaxy, and found several candidates with chemical compositions suggesting they formed from nearly pristine primordial gas. The oldest confirmed stars are estimated to be nearly as old as the universe itself, with ages approaching 13 billion years determined from their compositions and positions on stellar evolution tracks. However, finding true population 3 survivors has proven elusive, possibly because even the smallest first stars were more massive than typical modern low-mass stars, due to the different cooling conditions in pristine gas. The search for living relics from the cosmic dawn continues with improved spectroscopic surveys. If found, these ancient stars would provide direct windows into conditions in the early universe. Black holes could carry imprints of the universe's first moments. Primordial black holes, if they exist, are hypothetical black holes that formed not from stellar collapse, but from the extreme density fluctuations in the very early universe, potentially during or just after inflation. These ancient black holes would carry information about conditions in the first moments after the Big Bang, providing unique probes of physics at energy scales impossible to recreate in laboratories. The mass distribution and abundance of primordial black holes would reflect the spectrum of primordial density fluctuations and the physics of any phase transitions in the early universe. If inflation produced regions of sufficiently enhanced density, primordial black holes could have formed with a wide range of masses from tiny fractions of a gram to thousands of solar masses. The smallest primordial black holes would have already evaporated through Hawking radiation, while larger ones would persist to the present day and might contribute to dark matter. Detecting primordial black holes through gravitational waves, gravitational lensing, or their effects on the cosmic microwave background would revolutionize our understanding of the early universe. These cosmic time capsules, if discovered, would be our most direct window into the first instance of creation. Primordial black holes could be as small as atoms or as heavy as mountains. The mass of primordial black holes could span an extraordinary range depending on when they formed in the early universe, from tiny black holes smaller than an atom to those weighing as much as mountains or even stellar masses. A black hole with a mass of about 100,000 kilograms would have a size comparable to a proton, demonstrating how extreme density is required to create these objects at small scales. Such tiny primordial black holes would have formed when the universe was just a fraction of a second old, during epochs when the cosmic density was high enough for even small overdense regions to collapse. Black holes formed at later times would be progressively more massive, with those forming at 1 second having roughly the mass of Earth. Stephen Hawking calculated that the smallest primordial black holes should have already evaporated through the quantum process, now bearing his name, but black holes above about 1 billion kilograms would survive to the present. The search for primordial black holes across this vast mass range employs many different techniques depending on the expected mass. The diversity of possible primordial black hole masses reflects the rich physics of the early universe. Black holes may influence the fate of entire galaxies. Supermassive black holes at the centers of galaxies are now understood to play crucial roles in regulating the growth and evolution of their host galaxies through a process called feedback. When gas falls toward the central black hole, it forms an accretion disk that heats to extreme temperatures and can launch powerful jets of particles and radiation extending far beyond the galaxy itself. This energy output can heat surrounding gas, preventing it from cooling and forming new stars, effectively regulating the galaxy's star formation rate. In massive galaxies, black hole feedback is thought to be responsible for shutting down star formation and transforming actively star-forming galaxies into quiescent systems. The correlation between black hole mass and galaxy properties suggests a co-evolution in which black holes and galaxies grew together, each influencing the other. Galaxies that lack central black holes or have undersized ones evolve differently, demonstrating the importance of this relationship. The cosmic ecosystem connecting the smallest central objects to the largest galactic scales remains a frontier of astrophysical research. Black holes might merge often enough to reshape galaxies. When galaxies merge, their central supermassive black holes eventually sink toward the center of the combined galaxy and may themselves merge after millions or billions of years of orbital decay. These black hole mergers release enormous amounts of energy in the form of gravitational waves that ripple outward through spacetime at the speed of light. The gravitational wave signal from merging supermassive black holes would be much too low in frequency for current detectors, but is a primary target for future space-based observatories and pulsar timing arrays. Evidence for these mergers is now emerging from pulsar timing experiments that detect the cumulative background of gravitational waves from many such events throughout cosmic history. The dynamics of black hole mergers can eject the resulting black hole from its galaxy entirely if the gravitational waves are emitted asymmetrically, creating wandering supermassive black holes in intergalactic space. The merger history of black holes is intimately connected to the merger history of galaxies throughout cosmic time. Understanding how often and how efficiently black holes merge provides insights into both gravitational physics and galaxy evolution. Hawking radiation could one day evaporate black holes. In 1974, Stephen Hawking made a remarkable theoretical discovery. Black holes are not completely black, but emit a faint glow of radiation due to quantum effects near the event horizon, causing them to slowly lose mass and eventually evaporate entirely. This Hawking radiation arises from the creation of particle-antiparticle pairs near the event horizon, with one particle falling into the black hole while the other escapes, carrying away energy. The temperature of Hawking radiation is inversely proportional to the black hole's mass, meaning smaller black holes radiate more intensely than larger ones. For stellar mass black holes, Hawking radiation is utterly negligible, far colder than the cosmic microwave background, and would take unimaginably long times to cause any significant evaporation. However, tiny primordial black holes with masses below about 1 billion kilograms would have already evaporated during the history of the universe. A black hole in its final moments would radiate with ever-increasing intensity, ending in a brilliant flash as the last of its mass converts to energy. Hawking radiation has never been directly observed due to its extreme weakness, but it represents one of the rare theoretical connections between quantum mechanics, gravity, and thermodynamics. White holes are a possible mirror image of black holes. White holes are hypothetical objects predicted by general relativity as the time reverse of black holes, regions of spacetime that cannot be entered but only exited, spewing matter and light outward rather than consuming it. Mathematically, white holes emerge from the same equations that describe black holes, representing another valid solution to Einstein's field equations. If black holes are cosmic drains, where matter falls in and information is trapped. White holes would be cosmic fountains, where matter emerges without any incoming path. Despite their mathematical existence, white holes have never been observed, and most physicists doubt they can form naturally in our universe. Some speculative theories propose that black holes in our universe might be connected through wormholes to white holes in other universes, with material falling into a black hole emerging through a white hole elsewhere. The Big Bang itself has sometimes been compared to a white hole, a singular event from which all matter emerged and into which nothing can fall. White holes remain fascinating theoretical constructs that highlight the rich mathematical structure of Einstein's theory. Gravitational waves carry whispers of ancient collisions. Gravitational waves are ripples in the fabric of space-time, produced when massive objects accelerate, predicted by Einstein's general relativity in 1916, and directly detected for the first time in 2015 by the LIGO Observatory. The first detected gravitational waves came from the merger of two black holes, roughly 1.3 billion light-years away, objects that spiraled together over billions of years before finally colliding in a fraction of a second. During the final moments of in-spiral, the two black holes converted about 3 solar masses of energy into gravitational radiation, more power than all the stars in the observable universe combined, yet the waves reaching Earth stretched space by less than 1,000th the width of a proton. Since that first detection, gravitational wave observatories have detected dozens of mergers, including black hole pairs, neutron star pairs, and mixed systems of black holes and neutron stars. Each detection carries information about the masses, spins, and distances of the merging objects, opening a new window on the universe invisible to telescopes that detect electromagnetic radiation. The chirp of gravitational waves from merging compact objects represents a new way to listen to the cosmos. These ripples in space-time carry messages from cataclysmic events that would otherwise remain forever hidden. Ripples in space-time could be fossils from the very first instant. Among the most sought-after cosmological signals is the imprint of primordial gravitational waves generated during cosmic inflation, ripples frozen into the fabric of space-time within the first fraction of a second after the Big Bang. If inflation occurred as theorized, it would have produced a background of gravitational waves stretching across the universe, leaving a distinctive pattern in the polarization of the cosmic microwave background radiation. This pattern, called B-mode polarization, would provide direct evidence that inflation happened and reveal information about the energy scales involved. Despite intensive searches, conclusive detection of primordial gravitational waves remains elusive, with earlier claims of detection later attributed to dust in our galaxy. Future experiments with greater sensitivity and improved foreground removal continue the hunt for this fossil signal from the universe's birth. The amplitude of primordial gravitational waves would tell us about the physics of inflation at energy scales impossible to probe in any laboratory. Detecting these ancient ripples would be among the most significant discoveries in cosmology, providing a direct window into the first moments of existence. The universe may still echo with the first gravitational waves. If inflation or other early universe processes produced gravitational waves, a stochastic background of these ancient ripples should still pervade all of space, a cosmic gravitational wave background analogous to the cosmic microwave background for light. This background would consist of gravitational waves from the entire history of the universe, superimposed into a random, continuous hum. Pulsar timing arrays, which use the precise radio signals from distant pulsars as cosmic clocks, are now detecting evidence consistent with such a gravitational wave background, though the source could be merging supermassive black holes rather than primordial signals. Space-based gravitational wave observatories planned for future decades will probe different frequency ranges, potentially detecting backgrounds from other cosmic sources. Distinguishing primordial gravitational waves from those produced by astrophysical events requires characterizing the frequency spectrum and statistical properties of the background. The universe's gravitational memory of events from the first moments through to the present may all be encoded in this pervasive background. Deciphering this gravitational echo represents one of the great challenges for the next generation of cosmological observations. Neutrinos from the first second of creation are still streaming through your body. In the first second after the Big Bang, the universe was hot and dense enough for neutrinos to interact frequently with other particles, maintaining thermal equilibrium with the primordial plasma. As the universe expanded and cooled past about 1 second after the Big Bang, neutrinos decoupled from other matter and began streaming freely through space, forming a cosmic neutrino background that pervades the universe to this day. These ancient neutrinos have been traveling for nearly 14 billion years, and now fill every cubic centimeter of space, with roughly 330 neutrinos per flavor. The cosmic neutrino background has cooled to a temperature of only about 2 Kelvin, slightly cooler than the cosmic microwave background photons. Right now, approximately 100 billion of these primordial neutrinos pass through every square centimeter of your body every second, utterly unnoticed because neutrinos interact so weakly with ordinary matter. Detecting this cosmic neutrino background directly remains beyond current technology due to the incredibly low energies of these ancient particles. These ghost-like messengers from the first second carry information about the universe at an even earlier epoch than the cosmic microwave background. The cosmic neutrino background has never been directly seen. Although the cosmic neutrino background is predicted with high confidence based on our understanding of early universe physics, no experiment has yet directly detected these primordial particles, because their energies are incredibly low, and neutrinos interact so weakly with matter. The cosmic neutrino background decoupled from other matter about 1 second after the Big Bang, earlier than the photons of the cosmic microwave background, making it potentially a more pristine window into the earliest epochs. However, the same properties that allowed neutrinos to escape so early, their weak interactions, make them extraordinarily difficult to detect with current technology. Indirect evidence for the cosmic neutrino background comes from cosmological observations that show the universe contains the expected amount of relativistic energy density, and from precise measurements of primordial element abundances. Proposed experiments using special materials or novel detection concepts aim to eventually detect these ancient neutrinos directly, but this remains a major technological challenge. The cosmic neutrino background represents the oldest signal the universe can in principle send us, predating light by hundreds of thousands of years. When detection becomes possible, it will open a new window into the first moments of cosmic history. The most energetic particles in the universe may come from beyond our galaxy. Ultra-high energy cosmic rays are the most energetic particles ever observed. Individual protons or atomic nuclei traveling at nearly the speed of light, with energies millions of times greater than the most powerful particle accelerators can produce. A single ultra-high energy cosmic ray can carry as much kinetic energy as a baseball pitched at highway speeds, all concentrated within a single atomic nucleus. The origin of these extreme particles remains somewhat mysterious, though they likely come from the most violent events in the universe, such as active galactic nuclei, gamma-ray bursts, or the jets from supermassive black holes. At the highest energies, cosmic rays interact with the cosmic microwave background photons and lose energy over cosmological distances, limiting how far they can travel, a phenomenon known as the GZK cutoff. This means the most energetic cosmic rays must originate from within a few hundred million light-years, relatively nearby on cosmic scales. tracing individual cosmic rays back to their sources is challenging, because magnetic fields in intergalactic and interstellar space bend their paths. These mysterious messengers carry clues about the most extreme accelerators in the cosmos. Cosmic rays constantly shower Earth with particles from distant space. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that rain down on Earth continuously from sources throughout the galaxy and beyond. When these particles enter Earth's atmosphere, they collide with air molecules and create cascades of secondary particles called air showers that spread out as they descend. A single high-energy cosmic ray can produce millions of secondary particles in its atmospheric shower, detectable by networks of ground-based detectors. The flux of cosmic rays at Earth's surface is about 1 particle per square centimeter per second at modest energies, decreasing dramatically at higher energies. Cosmic rays are the primary source of natural background radiation at high altitudes and contribute to the radiation exposure experienced during air travel. The magnetic fields of the Earth and Sun modulate the cosmic ray flux reaching Earth, with solar activity reducing the flux by deflecting lower energy particles. These energetic visitors from the cosmos have bombarded Earth throughout its history, occasionally causing rare events like the creation of carbon-14 used for radiocarbon dating. The laws of physics may be slightly different in other universes. If the multiverse hypothesis is correct, and countless other universes exist beyond our cosmic horizon, the fundamental constants, and even the laws of physics may vary from one universe to another. String theory suggests there could be an enormously large number of possible vacuum states, perhaps 10 to the power of 500 or more, each corresponding to a different set of physical constants. In some of these other universes, gravity might be stronger or weaker, the masses of elementary particles might differ, or even the number of spatial dimensions could be greater or fewer than 3. Most of these alternative physical settings would be hostile to the formation of galaxies, stars, or life as we know it, making our universe one of the rare habitable islands in an infinite landscape. This anthropic reasoning explains why we observe the particular constants we do. We exist in a universe where complex structure can form, because only such universes produce observers to ask the question. The multiverse hypothesis transforms the apparent fine-tuning of our universe from a mystery requiring explanation to a selection effect in a vast ensemble. Whether this represents a profound truth or an untestable speculation remains one of the deepest debates in modern physics. Cosmic inflation could have created baby universes we will never see. In the framework of eternal inflation, our observable universe represents just one bubble that nucleated when a small patch of inflating space stopped inflating and transitioned to normal expansion. During inflation, quantum fluctuations constantly create new regions, where the inflaton field takes different values, and some of these regions continue inflating while others stop. The regions that continue inflating produce more inflating space that spawns yet more regions in an eternal self-reproducing process. Each bubble that forms where inflation ends becomes an independent universe, with its own Big Bang, its own cosmic expansion, and potentially its own set of physical constants. The space between bubbles continues inflating forever, ensuring that bubbles cannot contact or communicate with one another. Our universe, according to this picture, is just one among an infinite number of cousin universes separated by eternally inflating buffer zones. This infinite production of pocket universes transforms the cosmos from a single creation event into an ongoing, eternal process of universe birth. Whether any observational evidence could ever confirm or refute this picture remains uncertain. We may never know whether our cosmos is the only one. The multiverse hypothesis faces a fundamental challenge. If other universes are forever beyond our cosmic horizon, with no possibility of communication or observation, is the hypothesis even scientific? Traditional scientific method requires theories to make testable predictions that can be confirmed or falsified by observation, but other universes seem by definition unobservable. Some physicists argue that if a well-confirmed physical theory naturally predicts the existence of other universes, as inflation might, then we should accept the consequences even if direct verification is impossible. Others contend that untestable predictions lie outside the domain of science, regardless of how elegant the theory producing them might be. Ingenious proposals for indirect evidence include looking for signatures of bubble collisions in the cosmic microwave background, or finding statistical anomalies in the distribution of physical constants that would be expected in a multiverse. So far, no convincing evidence for or against other universes has emerged from observations. The question of whether we are alone in the deepest sense, whether our cosmos is unique or one of infinitely many, may remain forever unanswerable. Gravity may be weaker than it should be because it leaks into other dimensions. The weakness of gravity compared to the other fundamental forces has long puzzled physicists, since it is about 10 to the 36th power times weaker than electromagnetism, despite both being mediated by massless force carriers. Some theories with extraspatial dimensions propose that gravity appears weak because it spreads into dimensions beyond the three we can perceive, diluting its apparent strength in our observable realm. In these scenarios, the other forces are confined to a three-dimensional membrane or brain, while gravity alone can propagate through the full higher dimensional bulk. This explanation would require the extra dimensions to have specific sizes and geometries that hide them from our everyday experience, while still affecting gravitational physics. Experiments at particle colliders have searched for evidence of extra dimensions through missing energy signatures or gravitational effects at small scales, but so far no conclusive evidence has emerged. The Large Hadron Collider could potentially produce microscopic black holes if extra dimensions exist at accessible energy scales, though none have been observed. Whether gravity's weakness truly results from extra dimensions or has some other explanation remains one of the open questions in fundamental physics. The early universe may have birthed cosmic strings stretching across space. Cosmic strings are hypothetical one-dimensional topological defects that could have formed in the early universe during phase transitions as the cosmos cooled after the Big Bang, similar to cracks that form in freezing ice. These strings, if they exist, would be incredibly thin, perhaps smaller than an atomic nucleus in width, but could stretch across the entire observable universe with enormous mass per unit length. Cosmic strings would distort spacetime around them in unusual ways, creating double images of background objects and generating gravitational waves as they oscillate and interact. The search for cosmic strings has included looking for characteristic patterns in the cosmic microwave background, statistical anomalies in galaxy distributions, and gravitational wave signatures from string dynamics. So far, observations have placed upper limits on the abundance and tension of cosmic strings, but have not detected them definitively. If cosmic strings exist, they would be relics of particle physics at energy scales far beyond what accelerators can probe, providing unique windows into unified theories. These bizarre one-dimensional structures, stretching across galaxies, remain tantalizing hypothetical fossils from the universe's infancy. Some regions of space may have negative energy density. In classical physics, energy is always positive or zero, but quantum mechanics allows for the existence of states with negative energy density in limited regions of space and time. The Casimir effect demonstrates this phenomenon, where two closely spaced conducting plates experience an attractive force due to a reduction in vacuum energy between them, compared to the surrounding space. Negative energy density is required for certain exotic spacetime structures like wormholes and warp drives to exist according to general relativity, though whether such structures could ever form naturally or be constructed is highly uncertain. Quantum inequalities place strict limits on how much negative energy can exist and for how long, preventing the worst pathological consequences like time machines or infinite energy extraction. These constraints mean that while negative energy is real, it seems to be impossible to accumulate enough to create dramatic macroscopic effects. The study of negative energy connects quantum field theory with general relativity in ways that probe the boundaries of known physics. Regions of space with less than zero energy represent one of the stranger predictions of quantum theory. Wormholes are allowed by relativity but may never form naturally. Wormholes are hypothetical tunnels through spacetime that could connect distant points in the universe, providing shortcuts that bypass the normal light travel time between two locations. Einstein's general relativity permits wormhole solutions to its equations, with the simplest version connecting two black holes in different regions of space. However, these classical wormholes are unstable and would collapse faster than any signal could traverse them, unless held open by exotic matter with negative energy density. Even if stable wormholes could theoretically exist, there is no known natural process that would create them, and constructing one would require manipulating spacetime on scales far beyond any imaginable technology. Traversable wormholes might also create causality paradoxes if they connected points at different times, leading many physicists to suspect that unknown physics would prevent their use as time machines. The theoretical study of wormholes has value in understanding the limits and possibilities of general relativity, even if practical wormholes never exist. These cosmic shortcuts through the fabric of space remain science fiction for now, fascinating mathematical possibilities without observational support. Time may pass at different rates in different cosmic regions. Einstein's general relativity reveals that time passes at different rates depending on the local strength of gravity, with clocks running slower in stronger gravitational fields. Near the intense gravity of black holes or neutron stars, time passes measurably slower compared to regions far from massive objects. At a cosmic level, the varying density of matter across the universe creates subtle differences in the rate of time passage from place to place. Inside dense galaxy clusters, time runs slightly slower than in the nearly empty cosmic voids between filaments. During the early universe, when matter was compressed to much higher densities, time would have passed differently compared to the present epoch. These differences are subtle for typical cosmic structures, but become dramatic near extreme objects. The GPS satellites orbiting Earth must correct for relativistic time dilation to maintain their accuracy, as time passes faster at their altitude than on Earth's surface. Time is not an absolute cosmic backdrop, but a flexible quantity shaped by the matter and energy content of each region of spacetime. The scale of cosmic expansion stretches light into red. As light travels across the expanding universe, the space through which it travels stretches, and the light waves stretch along with it in a phenomenon called cosmological redshift. This is different from the Doppler shift caused by motion through space. Instead, the space itself is expanding and carrying the light waves apart. The further a galaxy is from us, the longer its light has been traveling through expanding space, and the more redshifted it appears. By measuring the redshift of a galaxy's spectral lines, astronomers can determine how much the universe has expanded since the light was emitted. The most distant galaxies and quasars show redshifts greater than 10, meaning the wavelength of their light has been stretched by more than a factor of 10 during its journey. The cosmic microwave background itself has been redshifted by a factor of about 1100, cooling its original orange glow to invisible microwaves. Cosmological redshift provides both a distance indicator and a direct probe of the universe's expansion history through cosmic time. A single photon could in theory stretch across the whole universe. The wave nature of photons means that a single photon does not have a precisely defined location, but rather exists as a probability distribution that can, in principle, extend over arbitrarily large distances. In the extreme case of the cosmic microwave background, photons have been traveling through expanding space for nearly 14 billion years, with their wavelengths stretching from about a micrometer, when emitted, to over a millimeter today. Quantum mechanically, each cosmic microwave background photon is described by a wave function that has had billions of years to spread out through space. However, when a photon is detected, its wave function collapses to a specific location, so we never directly observe these extended photon states. The uncertainty principle relates a photon's momentum, which is inversely proportional to its wavelength, to the uncertainty in its position, allowing low-frequency photons to have larger positional spreads. In the far future, as the universe continues to expand and photon wavelengths grow ever longer, individual photons could become incredibly spread out. The quantum nature of light allows single quanta to exist in superpositions spanning vast cosmic distances. Olbers' paradox asks why the night sky is dark. In the 19th century, German astronomer Heinrich Wilhelm Olbers articulated a puzzle that had troubled earlier thinkers. If the universe is infinite, eternal, and uniformly filled with stars, then every line of sight should eventually end on a stellar surface, making the night sky blazingly bright. Yet obviously the night sky is dark except for the stars and galaxies we can see. The resolution of Olbers' paradox comes from recognizing that the universe is neither infinitely old nor static. The finite age of the universe means light from extremely distant stars has not had time to reach us, and the expansion of the universe redshifts light from distant sources to longer wavelengths and lower energies. Additionally, stars have finite lifetimes and have not been shining forever. The darkness of the night sky is thus not a philosophical puzzle, but rather evidence that we live in a dynamic, evolving universe with a finite history. The cosmic microwave background represents the faint glow that does fill all of space but at wavelengths invisible to our eyes. The simple observation that night is dark carries profound cosmological implications. Matter barely won over antimatter in the beginning. In the hot, dense early universe, matter and antimatter were constantly being created and annihilating in pairs, converting energy to mass and back again in an equilibrium dance. If matter and antimatter had been created in exactly equal amounts, all of it would have mutually annihilated as the universe cooled, leaving only radiation and no material universe at all. Instead, a tiny asymmetry of roughly one extra matter particle for every billion matter-antimatter pairs allowed a residue of matter to survive the great annihilation. This minuscule excess, just about 1 part in a billion, is the origin of every atom, every star, every galaxy, and every living being in the observable universe. The physical mechanism that created this asymmetry, called baryogenesis, remains one of the great unsolved problems in physics. Theories require violations of certain symmetries between matter and antimatter at high energies, but the known sources of such violation appear insufficient to explain the observed excess. Understanding why matter won over antimatter is fundamental to explaining our very existence. Without that imbalance, no galaxies would exist. The survival of matter over antimatter in the early universe was essential for the formation of every cosmic structure we observe, from galaxies and stars to planets and living beings. If matter and antimatter had existed in perfect balance, their mutual annihilation would have converted all mass into radiation, leaving a universe filled with light, but devoid of atoms. No protons or neutrons would have survived to form atomic nuclei, no electrons would have remained to form atoms, and no atoms could have collapsed into stars and galaxies. The photons left behind from perfect annihilation would have continued to cool and stretch as the universe expanded, producing something like the cosmic microwave background, but with nothing else. The tiny asymmetry that allowed matter to survive represents one of the most consequential facts about our universe, determining that something rather than nothing would emerge to form complex structures. Without this imbalance, the cosmos would be an eternally expanding bath of cooling radiation, empty of meaningful structure. Our existence is owed to a subtle violation of symmetry whose origin we do not yet understand. The universe cooled as it expanded, allowing atoms to form. As the universe expanded after the Big Bang, its temperature dropped because the energy of particles and radiation became diluted across ever-increasing volumes of space. In the first 3 minutes, the universe cooled enough for protons and neutrons to fuse into the nuclei of light elements, primarily hydrogen and helium, in a process called Big Bang nucleosynthesis. However, the temperature remained too high for electrons to bind to these nuclei, leaving the universe filled with an ionized plasma that scattered light like fog. About 380,000 years after the Big Bang, the temperature dropped below about 3,000 degrees, cool enough for electrons to finally combine with nuclei to form neutral atoms in the epoch of recombination. This transition freed light to travel unimpeded for the first time, creating the cosmic microwave background we observe today. The continuing expansion and cooling allowed gravity to slowly assemble atoms into increasingly complex structures over the following billions of years. The cooling universe transitioned from a hot plasma to a gas of atoms to a cosmic web of galaxies, each step enabled by decreasing temperature. The cosmic microwave background is slightly lopsided. Detailed maps of the cosmic microwave background reveal that the universe appears to have a slight asymmetry, with one hemisphere of the sky having slightly stronger temperature fluctuations than the other. This hemispherical asymmetry was noted in data from the WMAP satellite and confirmed by the more precise Planck mission, though its statistical significance continues to be debated. If real, this asymmetry would challenge the fundamental cosmological assumption that the universe should look statistically the same in all directions on large scales. Possible explanations range from statistical flukes in a fundamentally symmetric universe to exotic physics involving preferred directions set during inflation. Some theorists have proposed that our universe might have a finite topology that creates the appearance of asymmetry, while others suggest influences from physics beyond our observable horizon. The hemispherical asymmetry remains one of several cosmic microwave background anomalies that collectively challenge the simplest cosmological models. Whether these anomalies signal new physics, or will eventually be explained by improved understanding of foregrounds and systematics, is actively debated in the cosmology community. A mysterious axis of evil aligns structures across the universe. Among the puzzling features in the cosmic microwave background is an unexpected alignment of the largest scale temperature patterns with each other, and apparently with features of the solar system, whimsically dubbed the axis of evil by cosmologists. The largest temperature multipoles in the cosmic microwave background appear to be aligned along a common axis rather than randomly oriented as simple cosmology predicts. This axis appears to correlate with the plane of the solar system and the direction of Earth's motion, which seems like an improbable coincidence if the cosmic microwave background truly represents primordial conditions unrelated to our local environment. Possible explanations include systematic errors, foreground contamination from our galaxy, or statistical flukes that would disappear with different analysis methods. More exotic possibilities suggest the alignment might reflect genuinely unusual large-scale structure in the universe or unknown physics affecting cosmological observations. The axis of evil remains unexplained after nearly 2 decades of study and multiple independent confirmations. Whether this mysterious alignment represents a genuine cosmological puzzle or an artifact of observation and analysis continues to intrigue researchers. Some galaxies may be racing toward a mysterious great attractor. Observations in the 1980s revealed that our galaxy and thousands of others in our cosmic neighborhood are moving toward a vast concentration of mass hidden behind the dust and stars of the Milky Way's disk, dubbed the Great Attractor. This mysterious gravitational source lies roughly 250 million light-years away in the direction of the Centaurus and Hydra constellations, where our galaxy's obscuring material makes observation difficult. Further studies revealed that the Great Attractor is itself being drawn toward an even larger concentration called the Shapley supercluster, one of the most massive galaxy clusters known. The collective motion of galaxies toward these mass concentrations is called peculiar velocity, representing deviations from the smooth expansion of the universe caused by the gravitational pull of nearby structures. Mapping these peculiar velocities across the cosmos reveals the distribution of mass and has helped trace the locations of previously unknown galaxy concentrations. The flow of galaxies toward the Great Attractor and beyond represents one of the large-scale gravitational dynamics shaping our cosmic neighborhood. Our galaxy is a small participant in this vast gravitational dance, spanning hundreds of millions of light-years. Dark flow hints at influences beyond our cosmic horizon. Some studies have claimed to detect an unexplained coherent motion of galaxy clusters toward a particular direction extending to vast distances, a phenomenon called dark flow that would suggest gravitational influences from beyond the observable universe. If real, dark flow would indicate that massive structures or unusual conditions beyond our cosmic horizon are tugging on matter within our visible universe. The effect was initially reported using the kinetic Sunyaev-Zeldovich effect, which detects the motion of hot gas in galaxy clusters through its distortion of cosmic microwave background photons passing through. However, subsequent analyses with different datasets and methods have yielded conflicting results, with some studies detecting similar signals and others finding no evidence for dark flow. The controversy highlights the difficulty of measuring small systematic motions across cosmological distances. If dark flow is genuine, it would have profound implications for our understanding of cosmic structure and possibly provide indirect evidence for a multiverse or pre-inflationary conditions. The question of whether the universe beyond our horizon is tugging at the matter we can see remains actively debated. The fine-tuning of cosmic constants allows galaxies to exist at all. The fundamental constants of physics, such as the strength of gravity, the masses of elementary particles, and the properties of nuclear forces, appear to be exquisitely fine-tuned to allow the existence of complex structures like galaxies, stars, and life. If the strong nuclear force were slightly stronger, all hydrogen would have fused into heavier elements in the Big Bang, leaving no fuel for stars. If gravity was slightly stronger, stars would burn too quickly for life to evolve, slightly weaker, and gas clouds might never collapse into stars at all. The cosmological constant, if larger by a factor of about 120, would have caused the universe to expand so rapidly that no structures could ever have formed. This apparent fine-tuning puzzles physicists, who debate whether it reflects a deep principle we do not yet understand, a selection effect in a multiverse where all values exist, or simply an observational bias, since we could only exist in a universe compatible with our presence. The coincidences required for our universe to host complex structure seem too numerous to be explained by chance alone. Fine-tuning remains one of the deepest mysteries at the intersection of physics and philosophy. The fate of the universe might depend on particles we haven't discovered yet. The ultimate destiny of the cosmos may depend on the properties of particles and fields that we have not yet discovered or even theorized, making predictions about the far future inherently uncertain. Dark energy, which currently drives the accelerating expansion of the universe, has unknown origin and properties that could change over cosmic time in ways we cannot predict. If dark energy strengthens, the universe might end in a big rip. If it weakens or reverses, a big crunch could follow. New particles with masses between the electroweak and Planck scales could affect the stability of the vacuum, potentially allowing the universe to tunnel into a lower energy state with catastrophic consequences. The discovery of the Higgs boson revealed that our vacuum may be metastable, meaning it could decay into a more stable state that would destroy all matter as we know it. The properties of dark matter, neutrinos, and hypothetical particles like axions could all influence cosmic evolution in ways we do not yet understand. The future of the universe may be written in the properties of particles awaiting discovery. The universe may be shaped by physics we haven't discovered yet. Our current understanding of the cosmos is based on the standard model of particle physics and general relativity, theories that have been spectacularly successful but are known to be incomplete. Dark matter is detected only through its gravitational effects, and we have no confirmed understanding of what particles or physics it represents. Dark energy is even more mysterious, a name for our ignorance about what drives cosmic acceleration rather than a physical understanding. The unification of general relativity with quantum mechanics remains elusive, with string theory, loop quantum gravity, and other approaches still lacking experimental confirmation. Near black hole singularities, and at the moment of the Big Bang, our current physics breaks down completely, signaling the need for new theories. The properties of neutrinos, the nature of inflation, and the origin of the matter-antimatter asymmetry all point to physics beyond our current models. The universe works according to rules we have partially deciphered, but deeper principles almost certainly await discovery. Some physicists believe the universe is a hologram. The holographic principle is a theoretical proposal suggesting that all the information contained within a volume of space can be encoded on its two-dimensional boundary, much like a hologram encodes three-dimensional information on a flat surface. This idea emerged from studies of black holes, where Stephen Hawking and Jacob Bekenstein showed that the entropy, or information content of a black hole, is proportional to its surface area rather than its volume. If black holes store information on their horizons, perhaps the same is true of any region of space, including the entire observable universe. The holographic principle has been made mathematically precise in certain theoretical contexts through the ADS-CFT correspondence, which relates gravity in a higher dimensional space to quantum field theory on its lower dimensional boundary. If the universe is truly holographic, then the three spatial dimensions we perceive might emerge from more fundamental two-dimensional physics at the cosmological horizon. This radical idea challenges our intuitions about space and reality, but remains a theoretical framework rather than an observationally confirmed fact. The holographic universe represents one of the most mind-bending possibilities in modern theoretical physics. Black holes may encode information on their surfaces. The information paradox poses a fundamental puzzle. When matter falls into a black hole, what happens to the information about its quantum state? Classical general relativity suggests information is lost behind the event horizon, but quantum mechanics insists that information cannot be destroyed. The resolution proposed by the holographic principle is that information about everything that has ever fallen into a black hole is encoded on the two-dimensional surface of its event horizon. The entropy of a black hole, which counts its possible internal states, is proportional to the area of its horizon rather than its volume, supporting this surface encoding picture. When a black hole evaporates through Hawking radiation, the information might somehow be released in correlations within the emitted radiation, though exactly how this works remains debated. Recent theoretical developments suggest that subtle correlations between the radiation and the black hole interior might resolve the paradox. The black hole information problem has driven some of the most important advances in theoretical physics over the past 50 years. These cosmic information processors may hold keys to understanding the deep connection between gravity and quantum mechanics. The holographic principle suggests reality is two-dimensional at heart. If the holographic principle is correct, the three-dimensional reality we perceive may actually emerge from more fundamental two-dimensional physics encoded on the boundary of space-time. This would mean that spatial depth is not a fundamental feature of reality, but rather an emergent phenomenon arising from the way information is organized on a distant two-dimensional surface. The idea finds precise mathematical realization in the ADS-CFT correspondence, where gravitational physics in a higher dimensional anti-de Sitter space is exactly equivalent to quantum field theory on the lower dimensional boundary. Physicists have used this correspondence to calculate properties of strongly interacting matter by translating problems into the language of higher dimensional gravity. Whether our own universe, which does not have anti-de Sitter geometry, is truly holographic, remains an open question. The holographic principle suggests that space and gravity might be emergent rather than fundamental, arising from more basic quantum information structures. This reconceptualization of reality, if correct, would represent one of the most profound changes in our understanding since general relativity. Space-time itself may be emergent from quantum information. Some of the most exciting developments in theoretical physics suggest that space-time and gravity are not fundamental aspects of reality, but rather emerge from deeper quantum information structures. In this view, the smooth fabric of space-time is like a macroscopic average of vast numbers of more fundamental quantum bits or degrees of freedom. The connections between regions of spacetime might arise from quantum entanglement between the underlying degrees of freedom, with more entanglement corresponding to regions that are closer together. This ER equals EPR conjecture proposes that the geometric connections called wormholes or Einstein-Rosen bridges are equivalent to quantum entanglement between particles. If spacetime is emergent, then at the smallest scales approaching the Planck length, ordinary notions of space and time would break down into something more fundamental. This paradigm shift would explain why gravity is so different from other forces. It might not be a force at all, but rather a consequence of how quantum information organizes itself. The emergence of spacetime from quantum entanglement represents a frontier where quantum mechanics, gravity, and information theory converge. Entanglement may link particles across cosmic distances. Quantum entanglement is a phenomenon where particles become correlated in ways that transcend classical physics, with measurements on one particle instantly affecting the properties of its entangled partner, regardless of the distance separating them. This correlation has been experimentally verified over distances exceeding 1,000 kilometers, and in principle has no upper limit, meaning particles on opposite sides of the universe could maintain entanglement. However, entanglement cannot be used to send information faster than light, because the correlation only becomes apparent when the measurement results from both particles are compared. Some physicists speculate that the cosmic microwave background photons might carry residual entanglement from their creation in the early universe, though detecting such ancient correlations is beyond current technology. If primordial inflation created entangled states that were then stretched to cosmological scales, the quantum correlations from the first moments might still pervade the universe. The connection between quantum entanglement and spacetime, suggested by the ER equals EPR correspondence, hints that these cosmic connections might be more fundamental than we realize. Entanglement weaves an invisible web of correlations across the cosmos. Entropy ensures the cosmos will one day reach heat death. The second law of thermodynamics dictates that entropy, a measure of disorder, and the unavailability of energy for useful work, always increases in isolated systems, and the universe as a whole is the ultimate isolated system. As entropy increases over cosmic time, the temperature differences that drive all processes gradually diminish, eventually approaching a state of maximum entropy where nothing can happen. This final state, called heat death, would see the universe become a uniform, dark, cold void, where no stars shine, no energy flows, and no events of any significance occur. The timescale for heat death is inconceivably long, with estimates ranging from 10 to the power of 100 years for all matter to decay, to even longer for quantum fluctuations to erase the last structures. In such a universe, time itself might become meaningless, since nothing would distinguish one moment from another. Heat death represents the ultimate fate of the cosmos, if dark energy continues to accelerate expansion forever. The inexorable increase of entropy makes this cooling, darkening end appear unavoidable, though the timescales involved dwarf all of cosmic history so far. Vacuum decay could, in principle, erase the universe instantly. Quantum field theory raises the unsettling possibility that our universe's vacuum might not be in its lowest possible energy state, making it metastable rather than truly stable. If the vacuum is metastable, it could quantum tunnel into a lower energy state, creating a bubble of true vacuum that would expand at the speed of light, destroying everything in its path. Within this bubble, the laws of physics would be different, with altered particle masses and force strengths that would dissolve all existing matter into something completely unrecognizable. Measurements of the Higgs boson mass suggest our vacuum might indeed be metastable, though the probability of decay is so low that the expected lifetime far exceeds the current age of the universe. Such a decay could be triggered by extreme conditions like those near black holes or cosmic strings, though no confirmed mechanism for triggering is known. If vacuum decay began somewhere in the universe, we would have no warning before the bubble reached us at light speed. This cosmic sword of Damocles, if real, represents the ultimate reset button that could rewrite the laws of physics without notice. A big crunch could one day reverse cosmic expansion. In the early decades of modern cosmology, one possible fate for the universe was the Big Crunch, a scenario where gravity eventually overcomes the expansion, causing the universe to contract and collapse back into an extremely hot, dense state, like a time-reversed Big Bang. This fate would depend on the universe's total mass and energy density exceeding a critical threshold, causing space-time to curve back on itself in a closed geometry. During the contraction, galaxies would begin approaching rather than receding, the cosmic microwave background would blue shift to higher temperatures, and eventually all matter would compress toward infinite density. The discovery of dark energy and accelerating expansion has largely ruled out the Big Crunch for our universe, since the acceleration seems to be driving galaxies apart forever rather than slowing expansion. However, if dark energy somehow reversed its behavior in the far future, contraction could still occur. Some theoretical models propose that the universe might cycle through multiple expansions and contractions, with big crunches followed by new Big Bangs. The Big Crunch represents a possible dramatic ending, rather than the slow fade of heat death. The Big Bounce could mean our universe is not the first. The Big Bounce is a theoretical scenario, proposing that the Big Bang was not the absolute beginning but rather a transition from a prior contracting phase, with the universe bouncing from contraction to expansion at extremely high but finite density. In this picture, a previous universe contracted toward a crunch, but quantum gravity effects prevented a true singularity and instead caused the universe to bounce into a new expanding phase. Loop quantum cosmology, approach to quantum gravity, naturally produces this bouncing behavior and predicts that our expanding universe emerged from a prior contracting one. If the bounce repeats, the cosmos might cycle eternally through expansion and contraction, with each cycle lasting perhaps hundreds of billions of years. Signatures of a pre-bounce epoch might be preserved in subtle features of the cosmic microwave background, or in the spectrum of gravitational waves. The Big Bounce offers an alternative to the singular beginning, suggesting that time might extend infinitely into the past through a succession of cosmic cycles. Whether our Big Bang was truly a fresh creation, or merely the latest in an eternal series of bounces, remains an open question. Some theories predict a cyclic universe that dies and is reborn. Cyclic cosmology proposes that the universe undergoes endless cycles of expansion and contraction, or expansion and renewal, with each cycle producing a new cosmic epoch, superficially resembling a new Big Bang. In some cyclic models, the universe expands, grows cold and empty over trillions of years, then somehow resets to begin a new hot, dense expanding phase. The ekpyrotic model proposes that cycles are triggered by collisions between higher dimensional branes, with each collision producing a new Big Bang in the lower dimensional space where we live. Roger Penrose's conformal cyclic cosmology suggests that the infinitely diffuse cold state at the end of an eon becomes conformally equivalent to the hot, dense state of a new Big Bang, with the universe eternally recycling. These cyclic models avoid the troubling question of what came before the Big Bang by positing an eternal succession of cosmic epochs. Different cyclic scenarios make different predictions for observable signatures, like gravitational waves and cosmic microwave background patterns. Whether the cosmos is a single finite story or an eternal cycle of renewal remains one of the deepest questions in cosmology. Galaxy clusters collide in slow-motion cosmic crashes. Galaxy clusters, the largest gravitationally bound structures in the universe, occasionally collide with one another in cosmic crashes that unfold over hundreds of millions of years. These cluster collisions involve thousands of galaxies, trillions of solar masses of dark matter, and vast clouds of hot intergalactic gas heated to tens of millions of degrees. When clusters collide, the individual galaxies pass through each other relatively unscathed due to the vast empty spaces between stars, but the hot gas from each cluster collides directly and heats up further, radiating intensely in X-rays. The dark matter halos of each cluster pass through one another like ghostly clouds, continuing on their trajectories, largely unaffected by the collision of the gas. These collisions provide natural laboratories for studying dark matter, gravity, and high-energy physics on scales impossible to reproduce in any laboratory. The Bullet cluster is the most famous example, showing the separation between gas and dark matter after a high-speed collision. Cluster collisions happen frequently enough that many merger systems have been identified, each telling stories of cosmic violence on the largest scales. Some galaxy clusters contain hot gas that outweighs their stars. The space between galaxies in massive clusters is filled with extremely hot diffuse plasma called the intracluster medium, gas heated to temperatures of tens to hundreds of millions of degrees by the cluster's gravitational potential. This hot gas is so sparse that it would qualify as a better vacuum than anything achievable in an Earth laboratory, yet there is so much of it that its total mass exceeds the combined mass of all the stars in all the galaxies of the cluster. The intracluster medium emits X-rays as electrons scatter off ions at these extreme temperatures, making galaxy clusters among the brightest X-ray sources in the sky, despite their ordinary light galaxies appearing unremarkable. This gas represents ordinary baryonic matter that fell into the cluster's gravitational well, but was too hot to cool and condense into stars and galaxies. Heavy elements produced in stellar explosions have been mixed throughout the intra-cluster medium over billions of years, enriching it with metals that provide diagnostics of the cluster's star formation history. The discovery that hot gas dominates the baryonic mass of clusters was one of the key insights revealing that most matter is not in stars. Galaxy clusters are primarily clouds of hot gas, punctuated by the relatively small concentrations of cooled matter we call galaxies. Some galaxies are so faint they are almost invisible. Astronomers have discovered a population of ultra-diffuse galaxies that are as large as the Milky Way, but contain far fewer stars, making them so faint that they were largely overlooked until recent decades. These ghostly galaxies have surface brightnesses so low that they barely stand out from the darkness of the night sky, requiring deep, sensitive observations to detect. Some ultra-diffuse galaxies appear to contain very little dark matter, which challenges standard models of galaxy formation, while others seem to be almost entirely dark matter with only a sparse scattering of stars. The origin of these diffuse systems is debated, with possibilities including failed star formation, tidal stripping by larger neighbors, or formation in particularly low-density environments. The Dragonfly telephoto array and other specialized instruments have revealed hundreds of ultra-diffuse galaxies in nearby galaxy clusters, suggesting they are far more common than previously thought. Some may represent a distinct mode of galaxy formation rather than failed normal galaxies. These dim stellar systems expand our understanding of the diversity of galaxies populating the cosmos. Giant elliptical galaxies may be the fossils of countless mergers. The largest galaxies in the universe are giant elliptical galaxies, massive spheroidal collections of stars found predominantly at the centers of galaxy clusters, containing trillions of stars and supermassive black holes weighing billions of solar masses. These enormous systems are believed to have grown through the successive merging of many smaller galaxies over billions of years, a process called hierarchical assembly. Each merger disrupts the ordered rotation of disk galaxies and randomizes stellar orbits, eventually producing the smooth ellipsoidal shapes characteristic of these giants. The stars in giant ellipticals are predominantly old and red, indicating that star formation has been quenched for billions of years, likely shut down by feedback from the central supermassive black hole. The most massive galaxies have grown primarily through the accumulation of smaller systems, rather than through in situ star formation. Detailed observations of stellar populations and chemical abundances allow astronomers to reconstruct the merger histories of individual galaxies. These cosmic leviathans represent the end point of galaxy evolution, the fossil record of countless earlier generations of galaxies. The Milky Way moves through space at over 1 million miles per hour. Our galaxy is in constant motion through space, traveling at approximately 600 kilometers per second, or nearly 1.4 million miles per hour, relative to the cosmic microwave background radiation. This velocity has several components, including the motion of the Milky Way within the local group of galaxies, the motion of the local group toward the Virgo cluster, and the larger scale flow toward the Great Attractor and Shapley supercluster. The cosmic microwave background provides a universal reference frame against which these motions can be measured through the dipole anisotropy, a slight temperature difference between the direction we are moving toward and the direction we are moving away from. Despite this tremendous velocity, the distances between galaxies are so vast that our motion is imperceptible on human timescales. It would take billions of years for our motion to significantly change our position relative to other major structures. The Milky Way has been falling through the cosmic web since its formation, part of the slow gravitational dance that shapes the universe's large-scale structure. We are passengers on a galaxy hurtling through the cosmos at speeds that dwarf anything in everyday experience. The universe is still ringing faintly with primordial vibrations. The early universe was filled with acoustic waves, pressure oscillations that propagated through the dense plasma in the first few 100,000 years after the Big Bang, and the imprints of these oscillations persist in cosmic structures today. These sound waves arose from the competition between gravity pulling matter together and radiation pressure pushing it apart, creating standing waves at specific scales called baryon acoustic oscillations. When the universe became transparent at recombination, these oscillations froze in place, imprinting a characteristic scale of about 500 million light-years in the distribution of matter. This scale appears as a preferred distance between pairs of galaxies, a cosmic ruler that astronomers use to measure the expansion history of the universe. The detection of baryon acoustic oscillations in galaxy surveys and the cosmic microwave background represents one of the most powerful tools in precision cosmology. These cosmic echoes allow measurements of dark energy properties and the geometry of the universe with remarkable accuracy. The universe continues to bear the imprint of the primordial sound that rang through it in its earliest epoch. The universe once glowed with plasma hotter than stars. In the first few 100,000 years after the Big Bang, the entire universe was filled with a plasma hotter than the surface of any star we see today, with temperatures starting above trillions of degrees and slowly cooling as space expanded. This primordial plasma was so hot that electrons could not bind to atomic nuclei, leaving photons constantly scattered and trapped in an opaque fog of charged particles. The temperature of this plasma far exceeded the core temperatures of stars, which typically range from about 10 to 100 million degrees for ordinary stellar fusion. As the universe expanded, this plasma cooled below about 3,000 degrees, allowing atoms to form and light to travel freely for the first time. The afterglow of this hot plasma is what we observe today as the cosmic microwave background, now cooled to just a few degrees above absolute zero. The contrast between the primordial inferno and the cold, dark universe of today illustrates the dramatic cooling driven by cosmic expansion. Every photon of the cosmic microwave background carries memory of this universal plasma that once glowed everywhere. Recombination ended that plasma age, making space transparent. Recombination is the name cosmologists give to the epoch about 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons and helium nuclei to form neutral atoms. This name is somewhat misleading since electrons had never been combined with nuclei before, but the term is borrowed from plasma physics, where similar processes occur. Before recombination, photons could travel only short distances before scattering off free electrons, making the universe opaque like a thick fog. After recombination removed most free electrons from the plasma, photons could travel essentially forever without scattering, and the universe became transparent. The cosmic microwave background represents the photons released at this moment of last scattering, carrying information about the conditions at recombination to our telescopes today. Recombination did not happen instantaneously, but occurred over roughly 80,000 years, as different regions cooled at slightly different rates. This transition from opaque plasma to transparent gas marked the end of the radiation-dominated era and the beginning of the structure formation epoch. Some of the most distant quasars are powered by billion solar mass black holes. The most distant quasars known shine from a time when the universe was less than 1 billion years old, yet their luminosities reveal supermassive black holes weighing billions of times the mass of our Sun already in place. The existence of such massive black holes so early in cosmic history poses a significant puzzle, since standard accretion processes seem too slow to grow black holes from small seeds to billions of solar masses in the time available. Possible solutions include the formation of massive seed black holes from direct collapse of gas clouds, super-Eddington accretion exceeding normal theoretical limits, or mergers of many smaller black holes. Each newly discovered high redshift quasar pushes back the frontier and constrains theories of early black hole formation. These ancient quasars represent the extreme end of a population that was far more common in the early universe, when gas supplies were abundant and galaxies were still actively forming. The light from these quasars has traveled for over 13 billion years to reach our telescopes, carrying information about conditions near the cosmic dawn. Understanding how these cosmic monsters grew so large so quickly remains a central challenge in astrophysics. Quasars act like lighthouses illuminating the fog of intergalactic gas. As light from distant quasars travels across billions of light-years to reach our telescopes, it passes through clouds of intergalactic gas that absorb specific wavelengths, imprinting absorption features that reveal the composition and distribution of matter along the line of sight. The Lebedistas, a dense thicket of absorption lines in quasar spectra, maps the distribution of neutral hydrogen in the intergalactic medium throughout cosmic history. By analyzing these absorption patterns, astronomers can trace the evolution of gas from the cosmic web, studying reionization, metal enrichment, and the growth of structure. Quasars serve as cosmic backlights, whose spectra carry information about every gas cloud between them and us, providing a record of cosmic evolution impossible to obtain by any other means. The technique has revealed that the intergalactic medium is enriched with heavy elements far from galaxies, showing that stellar explosions have polluted the cosmos on vast scales. Different types of absorption systems reveal gas in various environments, from the diffuse intergalactic medium to the dense halos of intervening galaxies. These cosmic lighthouses illuminate the otherwise invisible web of gas that connects galaxies across the universe. The universe's geometry may hold clues to its ultimate fate. The geometry of the universe, whether it is flat, positively curved like a sphere, or negatively curved like a saddle, is intimately connected to its ultimate destiny through Einstein's equations of general relativity. A universe with positive curvature would be finite in extent, and might eventually stop expanding and collapse, while a universe with negative curvature would be infinite and expand forever. Current observations indicate the universe is very close to perfectly flat, balanced on the knife edge between these possibilities, but with dark energy now dominating the expansion, the fate is set toward eternal expansion, regardless of slight curvature. Measurements of the cosmic microwave background, galaxy distributions, and supernova distances allow geometrical parameters to be determined with precision approaching 1%. The flatness of the universe was unexpected before inflation theory explained how exponential expansion would naturally produce a flat geometry. This geometrical property has profound philosophical implications, determining whether the universe has a definite total size or extends infinitely in all directions. The geometry of space-time, invisible and intangible, shapes the cosmic arena in which all events unfold. We may never know what lies beyond the cosmic horizon. The cosmic horizon defines the boundary of the observable universe, beyond which light has not had time to reach us since the Big Bang, and this boundary may forever limit our knowledge of the cosmos. Regions beyond the horizon are not in principle different from regions within it. They simply cannot be observed, because information travels at a finite speed in a universe of finite age. The accelerating expansion driven by dark energy makes this situation worse, as galaxies currently visible are being pushed beyond the horizon faster than new regions can come into view. In the far future, observers in our galaxy will see an increasingly empty universe as distant galaxies fade beyond detectability. We can make inferences about regions beyond the horizon based on the cosmological principle, the assumption that the universe is similar everywhere, but we can never directly test these assumptions. Some cosmological signals might carry indirect information about conditions beyond the horizon, but definitive knowledge seems impossible. The cosmic horizon represents an absolute limit to observation, a boundary beyond which the universe keeps its secrets forever. Creation itself began with imperfection. The universe we observe today, with all its galaxies, stars, and complex structures, owes its existence to tiny imperfections in the otherwise smooth early cosmos. If the universe had been perfectly uniform at the Big Bang, gravity would have had nothing to work with, and matter would have remained an ever-thinning fog without clumping into stars or galaxies. Instead, quantum fluctuations during inflation created tiny variations in density, regions that were slightly denser or slightly less dense than average by about 1 part in 100,000. These tiny seeds of imperfection were amplified by gravity over billions of years, growing into the cosmic web of galaxy clusters, filaments, and voids. Without these primordial imperfections, the universe would be a dark, featureless void, with no observers to contemplate it. The particular pattern of imperfections in our universe determined which specific structures would form where, making the detailed map of galaxies contingent on quantum events in the first moments. Creation required imperfection. Perfection would have been sterile. Every atom of carbon in your body may once have been born in ancient stars. The carbon atoms that form the backbone of every organic molecule in your body were created through nuclear fusion inside stars, forged when helium nuclei combined under immense temperature and pressure in stellar cores. This triple alpha process, in which 3 helium nuclei fuse to form carbon, occurs only in stars that have exhausted their hydrogen fuel and begun burning helium. The carbon produced in stellar interiors was released into space when these stars died, either through gentle stellar winds in red giant phases or through violent supernova explosions. This stellar debris mixed with interstellar gas clouds that eventually collapsed to form new generations of stars and their planetary systems, including our own solar system. The carbon now in your body has been through at least one stellar generation, possibly several, cycling through cosmic processes spanning billions of years. Every breath you take, every thought you have, is enabled by atoms cooked in nuclear furnaces that burned out before the sun existed. You are made of stellar ash, recycled stardust, temporarily organized into a form that can wonder at its own origin. The darkness of the night is not emptiness, but a canvas painted by time and distance. The darkness between stars when you look at the night sky is not empty void, but rather a canvas on which the finite age and expansion of the universe have painted their signature. Light from the most distant sources has been stretched to wavelengths invisible to our eyes and diluted by the expansion of space until only the most sensitive instruments can detect it. The cosmic microwave background fills the darkness with ancient light from the universe's first transparent epoch, shifted from visible glow to invisible microwaves. Between the visible stars, the blackness contains the light of billions of galaxies too faint to see without telescopes, their photons scattered thinly across the cosmic void. Neutrinos from the first-second stream through the darkness in unimaginable numbers, ghost-like and undetected. Dark matter pervades the emptiness, its gravitational influence shaping the galaxies we can see while remaining invisible itself. The night sky's darkness is thus filled with information, history, and matter, a rich tapestry painted by nearly 14 billion years of cosmic evolution. The universe is vast, and so are you. The scale of the universe staggers comprehension. with the observable region stretching 93 billion light-years across, containing 2 trillion galaxies, and each galaxy holding billions of stars. Yet you are a part of this immensity, constructed from atoms that trace their origin to the first moments after the Big Bang, and to the nuclear furnaces of countless stars. The complexity contained within a single human consciousness may be as profound as the complexity of cosmic large-scale structure, with roughly as many neural connections in your brain as there are stars in the Milky Way. You are not insignificant because you are small. Scale does not determine significance. The universe has organized itself over 14 billion years to produce beings capable of understanding and appreciating its vastness. In a very real sense, you are the universe becoming aware of itself, matter contemplating its own origin. The immensity of the cosmos is mirrored in the depth of the consciousness that can perceive it. To live in such a universe is to exist in wonder. Existing in a cosmos of such grandeur, mystery, and beauty is an extraordinary circumstance that perhaps only rarely occurs across the vast emptiness of space and time. We live in a universe where quantum fluctuations became galaxies, where stardust became thinking beings, where the laws of physics conspired to allow complexity and consciousness to emerge. The coincidences that permit our existence, the fine-tuning of constants, the matter-antimatter asymmetry, the formation of carbon in stellar cores, seem so improbable that wonder is the only appropriate response. Even if other universes exist with different properties, we find ourselves in one that crafted observers from chaos. To contemplate the cosmos is to participate in something remarkable, matter reflecting on its own origin, energy becoming aware of itself. The universe did not have to contain beings who could ask why it exists, yet here we are, fragments of the cosmos gazing back at the whole. To exist at all in such a place is to exist in perpetual wonder. And now the quiet wonders of cosmology begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths. From the fiery plasma of the first moments, to the invisible scaffolding of dark matter. From the ancient glow of the cosmic microwave background, to the silent ripples of gravitational waves still echoing through the fabric of existence. You have explored the birth of time itself, the stretching of space, and the haunting possibility that our cosmos is but one bubble among countless others. You are part of this story. Not just an observer, but the story itself. Every atom in your body was forged in ancient stars. Every breath you take connects you to the vast web of galaxies, stretching across billions of light years. You are made of the same matter that was born in the first moments after the Big Bang. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle expansion of the universe itself, like the patient drift of galaxies through the cosmic web. Tonight, as you rest, the cosmos continues its ancient dance. Galaxies drift through the dark, stars ignite and fade, and somewhere beyond our cosmic horizon, mysteries we may never understand unfold in silence. You are a small, warm presence within this infinite expanse, peacefully resting among the wonders of existence. Sleep well. Sweet dreams. And may you carry with you the quiet knowledge that you are woven into something vast and beautiful. A universe that began before time and stretches toward eternity. Thank you for joining me on this journey through the wonders of cosmology. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of science and our remarkable universe. There are more wonders waiting. More secrets hidden in the fabric of space-time, in the dance of black holes, in the glow of distant quasars. Rest well. and may the universe keep you company through the night. This has been Drowsy Discovery. Good night.